Okay, and you can see some for real in action here. I'll just give this a shake so you can tell what's going on. Okay, this is basically just a tank that's half full of water. Notice if the angle of incidence is 0, right? If it enters at an angle 0 relative to the normal of the interface between the two mediums, well, then the angle of refraction is 0, so it doesn't refract if it comes straight in, right? But as I start to tilt it and give it an angle of incidence, it's now entering water, okay? And so it's getting slowed down. And notice that. Notice how it's starting to bend more and more, right? It's getting slowed down. If you visualize the normal, well, you don't have to. It's that line there, right? Notice how on the other side of the water, where it enters the water, this angle right here between the normal is smaller than this angle right here before. The incident angle is bigger than the refracted angle because light is being slowed down. The index of refraction of water is higher. We can do the opposite, right? Notice something that's happening right now. That's going to be important later. Notice how it's not even leaving. Okay. However, there we go. Now it is. Okay. But on the way out, since it's going from water to air, it's getting a speed boost, I think of it as. So notice now here, the angle between the normal, right here, right? That angle is now smaller than the angle of refraction. It's now bigger up here because it's gone faster. It's gone from something with a higher index of refraction, a higher N, to a something with a lower N, right? And then as we go all the way, it gets back to the point where it doesn't care because the angle, well, it cares, but the angle of incidence is 0, and so the angle of refraction is 0, right? Pretty cool. You can see it in action there. Definitely bending. Okay, so our last topic for the week is dispersion and also total internal reflection. We'll cover them both today, okay? But essentially, this idea of dispersion, okay, was first noticed by Isaac Newton, not Pink Floyd, contrary to popular belief, okay? And it depends on the fact that every wavelength, we're coming back to something we mentioned earlier, every wavelength of light actually has a slightly different index of refraction, okay? Think of it like every wavelength gets slowed down slightly more or less by glass. So red light actually handles refraction better than violet light. Violet gets thrown off more, okay, in that order, from red to violet, going by the spectrum. Okay, so as you might recall from grade 8, this would be white light entering, okay, and white light is actually what you get when you put the rest of the colors together. So if you combine every color, okay, you get white. Okay, now you can separate white light back into its component colors by refracting it, by saying, okay, I'm gonna bend the white light, and I know that the red part of the white light will bend less than the violet part of the white light, so what you end up getting is a spectrum produced. You can actually split the white light into its spectrum. It's pretty cool, right? Think about it. What you're doing there is sorting EMR based on its refractive index, okay? The N we've been using, the fact that each wavelength has a slightly different index of refraction, the N we use, the common Ns on your table, are based on a sodium emission light, which is essentially just a very specific yellow type of light, okay, it's a very specific wavelength. Technically, they all have their own. So important to know that red refracts least, bends the least, blue refracts the most, okay? And you can think of it with Snell's law. So you have that lambda 1 over lambda 2 equals sine theta 1 over sine theta 2. If we solve that for sine theta 2, it equals lambda 2 over lambda 1 times sine theta 1, okay? Which just means the shorter the wavelength, right, the smaller the new angle. In other words, the shorter the angle, the more it has bent towards the normal, right? So you can kind of see that happening here, right? Red did bend away, but it bent away the least, right? And then again here, so it goes both ways, right? Whereas violet bent like whew, almost did a U-turn, right? And then again when it left. So I'll show you dispersion in action really quick. Okay, so I'll show you my setup. Right, what I have here is a ray box. Okay, so that takes light and focuses it into one ray. Okay, and then I have a prism, right? So what we can do is refract this white light, which again is made up of all colors, right? You can see it there. See that refracted ray coming out? Okay. Now to get it to show up, I have to give it some room to spread out a little bit more because we've changed its trajectory, but the farther it goes, the farther it spreads out, right? So I'm just going to actually, okay, Believe me, no funny business here. I'm just going to see, I'm going to get it, that refracted ray on this screen. And then what I'll do is I'm actually going to pick you guys up. Okay. And then look. So as I go back, hopefully it shows up as I get farther. Look at that. Do you notice how, I guess from your perspective, it would be the top is getting red, is looking more red, right? So I've split that white light, that beam of white light, into its constituent colors, the colors that make it up. Now, see that rainbow from red to blue, right? You can see green and yellow, all of them are in there. Pretty cool. Okay, now of course, this applies to infrared. So this lamp is probably pretty hot, so it probably is putting on some infrared radiation. That would be up here above the red. It's definitely not, it shouldn't be hot enough to produce UV, but if it did, that UV would be down here or beyond the violet, right? Ultraviolet. Pretty cool. Pretty cool. Okay, so important to be able to do this, okay? I'm gonna go ahead and do one for you. You try the other one, okay? So let's go ahead and figure out what will this look like. So first things first, before you try refracting anything, always draw your normal. So perpendicular to the surface at the point of incidence. Now, we'll do each color, okay? So white, if this is white light is incident on this prism, okay? We're gonna assume this is glass, as prisms always are pretty much. Red light is going to get bent, right? It still is getting slowed down. It's just the least effective of all of them, okay? Then we could have, I mean, honestly, they often leave orange out, but why not? It'll look prettier. Okay, orange is bent a little bit more. Yellow is bent a little bit more. Ooh, green was maybe a bad color to pick for my normal. Definitely green was a bad color to pick for my normal. Let's make the normal black. Okay, what bends a little more than green? Roy G. Biv. Biv is blue. Okay, blue bends a little more than green. And what bends the most out of the visible light anyway? Violet. Okay. After that, don't forget, now it's going to refract again on its way out. Okay, so draw your normals because each one has its own normal because it's leaving at its own point. Okay. Now, right now it's going from a higher index of refraction to a lower index of refraction, right? It's going to air where it's going from glass to air. So it's going from a higher index of refraction where it goes slower to a lower index of refraction where it's going to go faster. So now they're going to bend away from this new normal. So you can see how that makes this effect even more pronounced, right? So now this red light is going to bend away, but not as much. Is going to bend away, but not as much as the orange light, which is going to bend a little more, but not as much as the yellow light, which is going to bend more, but not as much as the green light, which is going to bend even more than that, not as much as the blue light, which is going to bend even more than that, and not as much as the purple light, which is going to bend even more than that. Okay, and so what you can get, just like we did on our screen there, right, is a nice, beautiful, continuous spectrum of red to orange, yellow, to green, to blue, to violet. Okay, I'll let you go ahead and try this other one on your own, but I'll post it in the notes so you can check your work. Okay, now does light always refract? Well, does light always refract when going from one medium into another, at least where they travel at different rates? No. So as light leaves a less dense medium to enter a more dense medium, so for example, air into water, in other words, N2, the new one, okay, it is more dense, so it slows down light more, right? In other words, it gets slowed down. When light slows down, yes, it will always refract as long as it's on an angle, okay? But when it goes the other way, okay, as light leaves a more dense medium to enter a less dense medium, oops, refraction always occurs. So when N2 is less than N1 and light speeds up, okay, refraction or reflection may occur. Truthfully, they both occur in both. It's just which one dominates, okay? So as light leaves a more dense medium to enter a less dense medium, refraction or reflection may occur. They both do. It's just one will dominate. We'll get a little bit into the math of why this happens in a sec, but let's just take a look at this diagram, right? If we have a light source that's below water, so it's leaving the water, it's going into it's getting a speed boost, it's going into a faster material where N2 is lower than N1, okay? Notice what happens as we increase the angle, right? As we increase the angle here, so therefore we increase the angle of incidence, okay, to our normal line, right? There's a certain point where it no longer actually refracts. It no longer actually leaves and enters. As the angle gets bigger and bigger, there's a certain point where the light gets completely reflected. Now, I want you to think about it this way. What is happening to the refracted angle? Well, as theta I gets bigger, because it's going into a less dense medium, right? It's speeding up. So it's bending more and more away from the normal, right? So as theta I is getting bigger, so too is theta R, right? As theta I gets bigger, theta R gets bigger. Eventually, we're going to get to the point where theta R becomes 90, right? Theta R becomes 90, and light that tries to leave gets shot along the surface of the, let's say, water, to simplify things, shot along the surface of the water, right? Once we go beyond that, if theta R were any bigger, we would actually have light doing the U-turn. So instead, it doesn't do that. It just reflects more and more. Truthfully, some always gets reflected, but the reflected beam completely takes over once we are past this angle, theta C, where that 90-degree refraction happens. And we call that angle the critical angle. Beyond the critical angle, if you're above the critical angle, you will not have any refraction. It'll all be reflected inwardly. So just to quickly summarize here before we do it, kind of go in a bit more depth. So theta C, also known as the critical angle or theta critical, okay, is the incidence angle that causes theta 2 or refracted theta, okay, to be 90 degrees. If you go above that, guess what? No more refraction, right? If you're below that, you're okay. A little bit is refracted. If you're right there, it technically gets refracted. It gets shot right along parallel to the interface between the two media. So if theta incidence, if the incident angle is less than the critical angle, you get mostly refraction. If the incident angle is equal to theta critical, you get that theta 2 or theta refraction equals 90 degrees, okay? And if theta, the incident angle is greater than the critical angle, you get what's called total internal reflection, where nothing escapes that substance, that doesn't leave the water at all, it stays in there. Okay, so it's back. I'll show you, okay? So notice what just happened there. What do you think that is, right? There is the critical angle, right? Some refracts, it's looking more and more is reflected, right? So as I start here, as I increase the angle, right, you'll notice the refracted ray gets dimmer and dimmer. The reflected ray starts to get brighter and brighter. Notice that, okay? Until eventually you hit that point where it's 90 and boom, no more refracted ray at all. It's all reflected, right? It hits 90 and then it's all reflected. Total internal reflection, right? No light is leaving the water interface. Notice though, we can't do it the other way. Okay, we can't do it the other way. There is no critical angle here. No matter what, a little bit will always be refracted, right? Until I actually go under the medium again. Okay, so again, when light travels from a slow to a fast medium or a high to low end, there are two rays, okay, like we just saw, the reflected ray where theta I equals theta R, and a refracted ray which bends away from the normal. Okay, this is confusing. Here it's talking about reflection, here it's talking about refraction. Usually that should be a capital R for refraction. Okay, but what happens when the angle of incidence is increased? Well, as we've seen, right, if we increase the angle of incidence enough, eventually the angle of refraction, right, eventually the angle of refraction is 90 degrees. If theta refraction, if the refracted angle is 90 degrees, then this is kind of just summing up, the incident angle is called the critical angle. So beyond that angle of incidence, you don't get any refraction. It's total internal reflection. And so if the angle of incidence is greater than the critical angle, then there is no refracted ray, only reflection. In other words, total internal reflection. Okay, so total internal reflection cannot occur when the ray goes from fast to slow, like we just saw, right? When it went from air to water, there was no point at which we didn't have any refraction. Okay, so why does that happen? Let's think about that. Well, when we were going from water to air, it was bending away from the normal, right? So theta R, the refracted angle, was getting bigger and bigger and bigger and bigger until it hit 90, and at that point, there's no more light leaving, right? However, when it goes from a fast medium to a slow medium, it bends towards the normal, right? When light gets slowed down, it bends towards the normal. So it doesn't matter what your theta I is, there's still a little bit of refraction. It doesn't matter what your theta I is, right? It's not going to bend to the point where it hits 90 and can't leave. It's bending towards the normal, right? So no matter what, as it's leaving, right? If there's your normal, doesn't matter if it's going to speed up and bend towards the normal, okay? So what? So it bends that way? It bends more out of the surface, right? It's not bending into the surface like we have when it goes the other way. All right, what is the critical angle between water and glass? So between any two interfaces, there's a critical angle. Draw a diagram to accompany the solution. So we should start with a diagram, okay? If we have glass and water, okay? We're looking for what's the critical angle? It's where the refracted angle equals 90 degrees, right? So let's see if we can find it. Let's start out by thinking about that. Okay, so I'll draw normal, but now we have to think about, is this ray going from glass to water or water to glass? If we're trying to find the critical angle, remember, it has to be speeding up, right? It has to be bending away from the normal to get to that 90-degree angle. So where will it go faster, water or glass? Right. Glass has a higher index of refraction, which means it slows light down more, which therefore means water lets it go faster. Okay. So to find a critical angle here, we need to think about it going from glass to water. Okay. That is going to be how it gets that's how it gets sped up, right? It needs to go from glass to water so that it can bend away from the normal towards 90. So this is what we want. We want theta refraction, or theta 2, right, to be 90 degrees. And we want to know theta incident when that happens, okay, or theta 1. So just a Snell's law, really, okay? N2 over N1 equals sine theta 1 over sine theta 2. And we're saying, what is theta 1 when theta 2 is, well, 90 degrees. So, okay, so sine theta 1 equals sine theta 2 times n2 over n1. So sine theta 1 equals sine of 90 degrees. If you remember your math class, you'll know that sine of 90 degrees is actually 1, okay, of 1.33 over 1.54. And so sine theta 1 is just going to be whatever 1.33 divided by 1.54 is. That's actually how you can calculate all critical angles, is by taking the ratio of their indices of refraction. So I got 0.8636, and then theta 1 is inverse sine of that. And so theta 1 equals, I got to 3 significant digits, 59.7 degrees. So let's interpret that for a sec. What does that mean? It means if you go beyond this angle, if you make theta I steeper than that, so if you go more and more this way, you are going to get total internal reflection. None of your light is going to actually leave and go into the water. Hey, guess what? You've actually seen this before, okay? Have you ever noticed in the ocean, right? Or let's say in the lake, if you're standing at the lake, right? Near you, you can see rocks and stuff at the bottom, right? You can see everything near you. But as you look out, can you see the bottom of the lake? No, right? And yes, part of that is that the light has a harder time reaching you from the bottom of the lake, but it's also due to this, right? As the angle increases, you can see less and less and less and less, okay? So even your friend just bobbing, if your friend is far enough out in the lake, right? If they're just bobbing just under the water, where it's not due to light not being able to reach you because there's not that much water between you, right? It's just because the light that's leaving your friend, who's just holding their breath just under the water, right? They're at a far enough angle that you can't see them. All you get is light bouncing off the top of water to your eyes, and the light that's trying to leave them and go to you is getting totally internally reflected. Okay, another example. Light passes from water out to air. Calculate the angle at which the light will leave the boundary if the angle of incidence is 12 degrees. So let's draw a quick diagram. Okay, draw in our normal line. And we have light leaving at an angle of incidence of 12 degrees. So theta 1 equals 12 degrees. Now, it's going from water to air, so is it going to speed up or slow down? It's going to speed up, which means it's going to bend away from the normal, right? I think of it as it's trying to get away from the normal. If it gets a speed boost, it will succeed in doing that. Okay, if it gets slowed down, it will fail and get sucked in. Theta 2, that's what we want to know. Okay, simple enough. So n2 over n1 equals sine theta 1 over sine theta 2. Okay, we've done this manipulation enough that I'm just going to jump to this. Okay, if you're not sure how I got there, you can go back and look. Okay, and so sine theta 2 equals n1 is 1.35, right? So 1.35 over the index of refraction of air is 1.00. That's on the back of your formula sheet, by the way, times sine of 12 degrees, the incident angle. So sine theta 2, I got 0.28068. The inverse sine of that is theta 2, and that is, I got 16 degrees. Okay, great. So that seems like an out of place question. Let's see what happens now if the angle of incidence is 75 degrees. Okay, I'm going to tell you something right now. That's way beyond the critical angle of water, air. Let's see what happens. Sine theta 2, again, equals n1 over n2. Jumping right to the manipulated version this time. Sine theta 1, okay, we have that sine theta 2 equals 1.35 over 1.00, okay, times sine of 75 degrees. So sine of theta 2 equals 1.30. And you might remember this from math class. Can you take the inverse sine of anything bigger than 1? No, it's meaningless, because remember, sine is opposite over hypotenuse, and hypotenuse is the biggest side of the triangle. So opposite over hypotenuse, opposite always has to be smaller than hypotenuse, right? So you can never have something bigger than 1 when you take the sine of it. So you will get an error. When you do sine to the negative 1 of 1.3, you will get an error. Why? Because we are beyond the critical angle, right? So error, because can't inverse sine something greater than 1, okay? So why? It reflected. It reflected totally and internally, TIR, okay? This one I'm going to actually just skip over. You can come back and look at my solution if you're curious. Honestly, it's just beyond what we need to worry about. It's a difficult problem, not because of the physics, but because of the geometry involved, okay? And it's probably not really worth our time right now. Okay, which brings us to the last thing for this week, a rainbow. Okay, so dispersions and critical angles, putting those together, that's how we get a rainbow. Okay, pretty cool. So you might not have noticed before, but now that I tell you, check. Every time for the rest of your life you see a rainbow, okay, the sun will be behind you, right? The sun will be behind you, and the rainbow will be off kind of in the distance. So the sun needs to be back here so that, okay, so sun behind you. Now, the sun emits white light, right? White sunlight comes in. This is a raindrop, drop top. Okay, that's a raindrop. Light comes in, it gets bent at the normal, but remember, blue light bends more than red. So, or violet bends the most, right? And then, aha, critical angle. Or I should say, that comes in beyond the critical angle. So what do you get? Total internal reflection. And then it gets reflected back to you, refracted more, and separated out. And it's had a long ways to go. So you get this beautiful spectrum, aka a rainbow. Okay, and that wraps up the last topic for this week. Just a reminder, blue refracts more than red. Okay, so for that topic, if you want practice specific to that, you can check the Google Classroom and agenda. And when you're feeling all good on everything this week, you can go ahead and try the weekly check-in. Okay, have a great weekend.